Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Today we will continue with more hands-on exercises. Today we will see T0 curve, T0 curve. Okay, so first we will see what is this T0 curve and why is it important, and then how to calculate it. So we have introduced about T0 curve in one of the previous classes. This is a G versus X diagram for a particular AB system, and alpha and phi are the two phases in that, and they join in this common tangent, and we take those points of common tangent, those compositions, and put them here and call it the two phase region and call that the tie line. And this is familiar to us, and we said this particular point is where Gibbs energy of phi and Gibbs energy of alpha both are equal, and this composition is going to be called as C0, meaning composition where at this temperature both alpha and phi have same Gibbs energies. Okay, and this composition point, if we translate it to the phase diagram against this temperature, it's going to be here, and if we repeat it, let's say between two phase region in multiple temperatures, we are going to get these different dots, all C0 compositions corresponding to different temperatures. Join all of them, we are going to get T0 curve, right? And this is what we did at various temperatures. Gx curves are plotted, and the compositions at which the Gibbs energies of the two phases are equal are traced on phase diagram. And this T0 curve is important to understand transformations like partitionless solidification, martensitic transformation, massive transformation, and so on. We said we will see about them in a future class. Now we will see them. We are going to explain the stuff based on this diagram, and what is important in these transformations is this: parent and product will have same chemical composition, parent phase and product phase will have same chemical composition and different crystal structures. This is very important. So without changing the chemical composition, phases transform. Allotropic transformations, in single element, as the phases can transform like that. As pure iron can entirely 100% iron can become BCC from FCC and FCC from BCC and so on. So that allotropic transformation is where chemical composition doesn't change. But what about the alloys? When you mix more than one elements together, can one phase transform to other phase without changing the composition? We'll see that. Okay. So think about this composition here and at this temperature, and if we take it to another temperature here in two different ways. One is by very slow cooling. If you do very slow cooling, it is expected that the phase diagram will be more or less followed, and we will have this alpha plus beta composition, alpha plus beta phases at the end, right, according to the equilibrium phase diagram. Now slow cooling results in alpha plus beta. Instead of this slow cooling, if we do fast cooling, okay, fast cooling in the sense a fast enough cooling can suppress all diffusion or nucleation of this beta phase itself. Okay, a fast enough cooling results in alpha or martensite. Composition of product is same as that of liquid, and crystal structure of product is different from that of liquid. Okay, so we are saying this liquid can become only alpha. Alpha's crystal structure, alpha is a solid, obviously it is going to have a crystal structure which is different from liquid, but the chemical composition is in this line, so it is not changing. So this kind of transformation can happen if the cooling rate is beyond certain level. Okay, why does that happen? So this need to happen. Equilibrium phases need kinetic support, example diffusion or partitioning of elements. What am I talking about? Partitioning of element is basically this. You see the composition of alpha and beta, at this temperature you can draw a tie line and figure it out, right? Now liquid has the overall composition which is very different from the alpha and beta composition. So if liquid has to become alpha and beta, the overall composition which is uniformly having this particular composition here this composition should become alpha of very low B content and very high A content, and beta of very high B content and very low A content, right? Meaning A and B element should interdiffuse for long range distances and become alpha and beta phases, right? So this more importantly, alpha and beta should also nucleate and grow. So these things are tough. If enough activation time is not available, this diffusion cannot happen and this kind of equilibrium phases cannot come. Now, in order to understand that why this is happening, so why only alpha will form, let's consider this temperature, and this is going to be the tie line. And how do we get this tie line from G versus X diagram? Let's bring that up. Three different curves are there: alpha, beta, and liquid. And there should be a common tangent between alpha and beta at this temperature. That's why we are getting these two phases at equilibrium. Now put the overall composition, this overall composition line here, and this is the common tangent which tells you alpha composition and beta composition to be in equilibrium. Now this liquid, when it is brought to this temperature fast, this entire G versus X is for this temperature. Okay, so at this temperature, what is the Gibbs energy of a liquid? It is here. Now this liquid would like to become alpha plus beta and attain this Gibbs energy, right? So this Gibbs energy is in the common tangent. So this is the Gibbs energy for the equilibrium system, meaning entire alpha plus beta mixture. This is going to be the Gibbs energy. Now, if beta cannot nucleate, the formation of these new phases, equilibrium phases cannot happen, then what is the next best thing that can happen in terms of Gibbs energy diagram? Now, this particular phase here, alpha, will have lower Gibbs energy compared to liquid, but not as low as this white dot. So, if the liquid cannot reach this Gibbs energy because alpha beta nucleation in these compositions is not possible, therefore the entire liquid transforms to this alpha, which is having lower Gibbs energy compared to the liquid and an entirely different crystal structure. So this is energetically becoming favorable, therefore this alpha phase can form. So this is partitionless solidification actually, because the composition of liquid does not change and no long range partitioning of elements happen. The liquid's composition is kind of frozen into the solid. Okay, so this is partitionless solidification, and this can happen in these sort of scenarios where alpha beta equilibrium phases cannot form, right? Now think about the T0 point or C0 point here, and to the right of it, if we have an overall composition, can this sort of phenomena happen? Let's consider the liquid's Gibbs energy. This is going to be the liquid's Gibbs energy. If this liquid is brought to this temperature, it should want to become alpha plus beta of this particular Gibbs energy. The combination of alpha and beta which will give this Gibbs energy, that's the equilibrium state. Now since this equilibrium state cannot be formed due to the kinetic restriction, can this liquid become alpha? If it becomes alpha, its Gibbs energy is going to go up to this point, right? So this is energetically unfavorable. So Gibbs energy increment cannot happen. So this liquid becoming alpha cannot happen. So partitionless solidification cannot happen to the points to the right of this yellow dot, meaning beyond the C0 point, you are not getting this partitionless solidification happening. Therefore, this point is going to tell you which are the compositions in which you can achieve this partitionless solidification. Okay. So if we put the dot here in the phase diagram, it's going to be here. And if we are going to get this kind of yellow dot for all the different temperatures, then how the alpha and the liquid C0 points will be? They all will be following this line, and that's going to be the T0 curve. So this T0 curve tells us that if your overall composition is cooled below this line, then there is a chance of achieving partitionless transformation. That's the biggest advantage of tracing this T0 curve. Okay. Now this is about the massive transformation. This is given here two different cases of massive transformation. The one in the right side looks similar to the one that we have seen in the previous slide. This is basically, we said alpha is going to form. This is telling something about the composition of that alpha. So let us not go into that. This level of covering the T-naught curve concept is good enough for us now. And here, if you see this beta, the high temperature is beta phase, and that can become alpha here completely, meaning entire beta transforms to alpha without changing the composition because of this partitionless nature of transformation, because it's some kind of a fast cooling, so it cannot become equilibrium phases. Okay, so this is non-equilibrium massive transformation because beta is becoming alpha instead of some two phases. Okay, so this is a non-equilibrium partitionless transformation. We are not using the word partitionless solidification because it's not the liquid where we start from. We start from another solid state beta. Therefore, this is a partitionless transformation or massive transformation. Okay, right here, this is beta, and if you slow cool it, alpha will nucleate out of it, and more alpha will form as you decrease the temperature, and at another temperature it's going to become completely alpha, right? So that microstructure will look different compared to if you take beta out of this temperature and put it directly into this temperature. Okay, it's more like cooling it rapidly. If you do that, then beta will transform to alpha at that temperature. That microstructure will be different. I mean, phase is still alpha completely, but the microstructural morphological features or the grain sizes, those things will be different. Okay, so this is a massive transformation which is equilibrium in nature, because alpha is an equilibrium phase. Okay, although the cooling does not go through all the equilibrium stages, the final phase achieved according to phase diagram, it is an equilibrium phase. Therefore, this is called as equilibrium massive transformation, right? So similarly, Martensite transformation can also happen in this similar sort of setup. Beta can transform to Martensite instead of alpha. That Martensite will have a different structure compared to alpha. That kind of transformations are also possible, and there you don't have any sort of diffusion. We call that military transformation, diffusionless transformations. That can happen. That is Martensite transformation. Okay. Now let's see how to make this diagram, T0 diagram, using the software. FENI system we will take. This system has this nice two-phase region where we can trace a T0 line. That's why we choose this. Calculate the T0 curve of FCC to BCC, FCC transforming to BCC completely through partitionless transformation. Okay, let's see how it let's see how to calculate that. This is the procedure in the software. Use graphical user interface. Open a new project. Select template property models. Okay, it's a template there, and in project window you will see tree of 5 steps, and system definer is one step where we have to select database and select elements, and we will create a successor to the system definer. We will create one more step ourselves, and we will call this we will use equilibrium calculator as a successor and change its name to phase diagram, and then perform calculation for FENI phase diagram. Meaning we will do a calculation for FENI diagram and keep it on one side, and then there is another step called property model calculator. There we will select T0 temperature. That's the model we are going to select, and then in the configuration window we will select one axis and select grid definition, which is more like selecting the axis here. Composition of nickel going from 0 to 30. That's the range where we have this two-phase field, 0 to 30% of nickel, and then select number of steps 30. 30 different stages is where this calculation will be done. And then in plot renderer stage, there will be one more step. We will delete that step. This is not required for this particular calculation. Delete table renderer and create predecessor, and then attach equilibrium calculator to that. That phase diagram that we change name to phase diagram we said for equilibrium calculator, that you can attach to this plot renderer, so that we will see both T0 and phase diagram in one diagram. Okay. Otherwise only T0 also we can plot if we skip this phase diagram step. To better understand this, we are putting the phase diagram also along with this. Okay, if you are a bit confused, let's see how to do that actually, then you will get it. Okay, so now this property models, the first one in the left side, I am clicking this one, property models. Okay, so we have these 5 different steps. 1, 2, 3, 4, 5. Actually, this my project is actually not a step. You can ignore that. Then system definer is where we are now. Here FE demo database is fine. We'll click FE and NI, 2 elements. FE and NI. So these are going to be our elements. Then click property. So then right click on system definer, create a new successor equilibrium calculator. So new successor is basically creating one more step in the tree, and which step we are going to create? An equilibrium calculator we are going to create. So click on equilibrium calculator. This is equilibrium calculator now, and change its name to rename to phase diagram. Okay, so we are going to keep a phase diagram here. Just for your understanding, this renaming is done. Okay, this phase diagram, where we are going to select this phase diagram button here, and then mass percent of nickel 0 to 100, that's fine, and temperature 500 is, we can change it to 298 to 2000. Okay, and then you can do click perform and keep it calculated. We don't need to plot it now, just click perform and let it calculate and keep the data for that. Okay, now calculation is done. Then the important one, the property model calculator. So click on that. Then you see multiple properties depending on the systems and all it is given. Here you can see general models, under which you can see T0 temperature. Okay, you can click on T0 temperature, right? And here you can see FCC as the first phase and second phase is BCC. Okay, this is important. Once you check that this is there, it's good enough. Other conditions you don't need to change now. And here in the calculation type, use one axis, and in grid definition use mass percent of nickel going from 0 to 30. Okay, 0 to 30, and in step sizes, and here in number of steps here, this also choose 30. Okay, this is important because if it calculates at different step sizes, the calculation may go slightly wrong. So better you choose this 30 here, and then click perform. Okay, now table renderer we can delete, we don't want it right now. Right click, remove, and if you see the plot renderer, you can see here this is only the T0 line. Okay, but if we make this phase diagram data as a predecessor to this, then phase diagram will also be superimposed there. So right click, add a predecessor phase diagram. This is basically the equilibrium calculator. Okay, and then click perform once again in the plot renderer. Okay, now you got phase diagram. This region I will try to label and show you what are these regions. Right click, add label, BCC-A2 is there on one side, and in this side we have FCC. Okay, so now what happened is, if we reduce the temperature slowly, it should become FCC plus BCC, but instead it can become single BCC provided we are below this blue line. This blue line is the T0 line. Okay, I can remove the in the phase diagram. You see both are here, property model calculator and phase diagram, both are there in the top. I'm clicking on phase diagram and removing the tie lines. Tie lines 0, legend option off. Okay, then click perform. You see, so within this 0 to 30 nickel content, this particular line is calculated. You can see that. So that is good enough for us. So therefore, you see all the compositions, C0 compositions and corresponding T0 temperatures are all here. So this tells you the limit of partitionless transformation in FENI system for FCC2 to BCC transformation. Thank you. I hope the lecture is useful. See you in the next class.